Right now, China's Tianwen-1 Mars probe is observing a jet structure extending 4 million kilometers from interstellar object 3I-ATLAS, appearing in irregular directions that contradict standard cometary behavior, leaving scientists unsettled. The images captured on November 9, 2025 from Martian orbit show what some researchers describe as an ion tail, sculpted by solar wind, but the configuration defies simple explanation. The jets do not radiate symmetrically from a nucleus, as solar heating would dictate. Instead, they twist at angles that suggest something more complex is happening beneath the surface of this enigmatic visitor from beyond our solar system. The object should not look like this. After swinging past the sun at perihelion, any normal comet would blaze with a magnificent tail, shedding billions of tons of vaporized ice and dust into space. Standard physics demands it. Calculations indicate 3I-ATLAS should have evaporated roughly 13% of its total mass during its close solar approach, releasing material equivalent to thousands of icebergs streaming behind it in a luminous banner millions of kilometers long. Instead, the object remains strangely compact. November 5th post-perihelion images showed no clear cometary tail. Harvard astrophysicist Avi Loeb noted the absence in his November 9th blog post, questioning whether the object might have fragmented near the sun. Updated observations confirm it survived intact, but something fundamental has changed. The object has accelerated unexpectedly and shifted to a bluish hue, marking what analysts believe is its third potential color transformation since detection. Here's where it gets interesting. That blue shift is not decorative. Spectral analysis suggests the color change may indicate irradiated carbon dioxide ice or exotic volatile compounds glowing under intense solar radiation, materials that form only in the frigid reaches beyond a star's snowline, where temperatures drop low enough for CO2 to freeze solid. The presence of such compounds in an interstellar traveler raises immediate questions about its origin environment. These ices require specific formation conditions found in the outer regions of protoplanetary disks, the swirling clouds of gas and dust that collapse to form solar systems. If 3I-ATLAS carries significant carbon dioxide ice, it was born in a system with chemistry and thermal gradients potentially very different from our own. The implications ripple outward from there. Scientists tracking the object have documented behavior that resists conventional categorization. Its brightness increased faster than models predict for typical comets. The light curve, the graph showing how an object's luminosity changes over time, climbed at a rate suggesting either unusual surface properties or internal processes not accounted for in standard cometary theory. Then there is the non-gravitational acceleration, a measurable change in velocity that cannot be explained by the sun's gravity alone. Comets often exhibit this when outgassing creates tiny rocket thrust effects, jets of vapor pushing the nucleus slightly off its calculated path. But 3I-ATLAS displays acceleration patterns that hint at mechanisms operating differently than expected. Some researchers propose hidden rock layers beneath the surface might be heating unevenly, releasing gas through fissures in asymmetric bursts. Others suggest the object's rotation could be interacting with its outgassing in ways not yet modeled. The data leave room for multiple interpretations, none entirely satisfying. Stop and consider that. An object arrives from interstellar space, survives a scorching pass near the sun without producing the expected tail, changes color multiple times, accelerates in ways that defy simple prediction, and ejects material in irregular directions. Each anomaly alone might warrant a footnote. Together, they form a pattern that demands explanation. NASA planetologist Emily Saunders put it plainly in recent communications with colleagues studying the object. This is like deciphering a fragment from another star system, where chemical and physical conditions radically differed from ours. The statement underscores the challenge. Researchers are not merely observing a comet. They are attempting to reconstruct the environment and history of an object that traveled through the galaxy for millions or billions of years before crossing paths with our solar system. The forensic task is staggering. Here's the problem. The conventional explanations keep hitting walls. If 3IATLAS is a standard interstellar comet, an icy body ejected from another star system and wandering the galaxy until gravitational chance brought it here, then its behavior should align reasonably well with what astronomers know about comets. The models have been refined over decades, calibrated against thousands of observations from short-period comets like Halley to long-period visitors from the Oort cloud. Those models predict how ice sublimates, how dust is released, how tails form and evolve. The models say 3IATLAS should have produced a spectacular tail. The models say its brightness should increase at a certain rate. The models say outgassing should create jets aligned with the sun's heating. The object is not following the script. When models fail, scientists look for missing variables. Perhaps the composition is unusual. Perhaps the structure is more complex. Perhaps the thermal properties differ. Each adjustment brings the model closer to matching observations. But with 3IATLAS, the adjustments are piling up, creating a Frankenstein's monster of special conditions needed to make the pieces fit. Think about what that means. Either the object is an outlier, an extreme case within the spectrum of natural cometary variation, or it represents something the current framework does not fully accommodate. The scientific community is wrestling with this tension in real time. On November 9th, Avi Loeb publicly speculated, carefully noting his comments were exploratory, that the jet structures visible in the Tianwen-1 images could resemble propulsion mechanisms or even navigational aids for a hypothetical spacecraft, though he emphasized natural explanations are far more likely. The statement generated immediate controversy. Critics accused him of sensationalism. Supporters argued he was merely exploring the logical space of possibilities. The debate itself reveals the discomfort. When a respected scientist from a prestigious institution suggests, even hypothetically, that an interstellar object might not be entirely natural, it signals that the conventional toolkit is struggling. Now about the data. The numbers matter. The jet structure imaged by Tianwen-1 extends up to 4 million kilometers from the nucleus. To grasp that scale, consider that the distance from Earth to the Moon is roughly 384,000 kilometers. The jets from 3IATLAS stretch more than 10 times farther than the Earth-Moon gap. If Earth were a marble, these jets would reach over 3 meters away. The structure is not a faint whisper. It is a massive feature carved by interactions between the object's outgassing material and the solar wind, the constant stream of charged particles flowing from the sun. The solar wind shapes cometary tails, pushing gas and dust into the characteristic curved arcs seen in classic images. But the Tianwen-1 data shows irregularities. The jets do not point uniformly away from the sun. They twist and diverge at angles inconsistent with a simple solar wind interaction. Either the object is rotating in a complex tumble, presenting different active regions to solar heating in unpredictable cycles, or the internal structure is far from uniform, with pockets of volatile material erupting sporadically as heat penetrates cracks and fissures. The greenish glow reported earlier added another layer of mystery. That particular hue typically indicates the presence of diatomic carbon molecules, a breakdown product of organic compounds being destroyed by sunlight. Comets often show green comas, the fuzzy clouds of gas surrounding the nucleus, because organic molecules in their ice matrices decompose under ultraviolet bombardment. The shift to blue observed after perihelion suggests a change in the dominant emitting species. Blue hues can arise from ionized carbon monoxide or carbon dioxide glowing in the solar radiation field. If the surface layers rich in organics have been stripped away by solar heating, exposing deeper ices with different chemistry that could explain the color transition. But it also raises the question, how stratified is this object? Comets are generally thought to be relatively homogeneous mixtures of ice and dust, primitive remnants of solar system formation. If 3I-ATLAS has distinct layers with different compositions, it suggests a more complex formation or evolutionary history. Scientists estimate the object's age at approximately 7.5 billion years. That number is not arbitrary. It comes from analyzing the trajectory and velocity, backtracking the object's path through the galaxy to infer when and where it might have originated. The Sun is 4.6 billion years old. The estimate places 3I-ATLAS formation more than 3 billion years before our solar system existed. The object is a relic from the early universe, from an epoch when the galaxy was younger. Stellar metallicity was different, and the first generations of planetary systems were still forming around stars with chemical compositions unlike the Sun's. The ancient age has profound implications. The material comprising 3I-ATLAS was forged in a protoplanetary disk billions of years ago, condensed into solid form under conditions set by the physics and chemistry of that distant environment, and then expelled into interstellar space to drift until now. It is a time capsule, potentially preserving information about star and planet formation processes from an era difficult to study directly. Here's where things get strange. A hypothesis circulating among researchers, discussed in professional correspondence and informal channels, proposes that 3I-ATLAS might not be a comet in the traditional sense. Instead, it could be a fragment of a destroyed exoplanet. The scenario goes as follows. Billions of years ago, in a distant solar system, a rocky planet formed beyond the snow line, accreting ice-rich material into a substantial world. Gravitational interactions with a giant planet in the same system, or perhaps a close stellar encounter, destabilized the orbit. The planet was torn apart by tidal forces or shattered in a collision. Fragments were scattered, some falling into the parent star, others ejected at high velocity into interstellar space. One of those fragments, 3I-ATLAS, wandered the galaxy for eons before chance brought it into our neighborhood. If true, the object carries within it the geology and chemistry of an alien world. Layers formed by planetary processes, perhaps altered by heat and pressure, in ways analogous to diagenesis on Earth, the physical and chemical changes sediments undergo as they lithify into rock. The hypothesis is bold, but it addresses several anomalies in one stroke. A planetary fragment would have a layered internal structure, explaining why outgassing might occur asymmetrically as different strata are exposed to solar heating. The presence of carbon dioxide ice is expected in bodies formed beyond the snow line of another star. The object's resistance to disruption during its solar pass makes sense if it has structural integrity beyond that of a loosely bound rubble pile, as many comets are thought to be. Emily Saunders' description of the object as a fragment from another star system aligns with this view, emphasizing the alien conditions encoded in its composition. Avi Loeb has noted that polarimetric properties, the way the object scatters light depending on orientation and surface texture, show unusual characteristics that might hint at a geology shaped by processes other than simple ice accretion. The trajectory passing relatively close to the ecliptic plane where the planets orbit is not proof of anything, but it adds a tantalizing detail. Objects scattered randomly from all directions should approach from any angle, yet 3I-ATLAS arrived roughly aligned with the solar system's disk. Read between the lines. The hypothesis of a planetary fragment is speculative, acknowledged openly by those discussing it, but the fact it is being discussed at all is significant. It means the standard cometary model is under strain. Most astronomers favor natural explanations rooted in unusual ice composition or structural quirks. Carbon dioxide ice sublimates directly from solid to gas, a process that can be invisible unless the viewing geometry catches the gas cloud just right. If 3I-ATLAS is rich in CO2 and poor in water ice compared to typical comets, it might outgas without producing a visible dust tail, creating what researchers call a stealth comet. Optical effects from the viewing angle could also mask a tail. Earth-based observers and spacecraft are looking from particular directions. A tail-oriented edge-on might appear much fainter than one seen broadside. Instruments like Hubble or the Mars Reconnaissance Orbiter might capture higher-resolution images that clarify the structure. But as of now, those data have not been publicly released, fueling speculation about what they might reveal. The object's resistance to solar flares is another point of intrigue. During its perihelion pass, 3IATLAS endured radiation and particle bombardment far more intense than anything experienced in the outer solar system, where it presumably spent most of its existence before arriving here. Typical comets can fragment under such stress. The nucleus heats unevenly, thermal expansion cracks the structure, and pieces break away. Comet Shoemaker-Levy 9 famously fragmented before colliding with Jupiter. Comet Ison disintegrated during its close solar approach in 2013. The fact that 3IATLAS emerged intact suggests either exceptional structural coherence or a composition that handles thermal stress differently. A rocky core wrapped in ice, or a matrix where rock and ice are intimately mixed at small scales, might distribute heat more evenly than a pure ice body, reducing the risk of catastrophic breakup. This aligns with the planetary fragment idea, where geological processes could have created a tougher, more resilient object. The upcoming close approach to Earth on December 19, 2025, at a distance of 270 million kilometers, presents a critical opportunity. For perspective, 270 million kilometers is roughly 1.8 astronomical units, nearly twice the Earth-Sun distance. The object will not be dramatically close, but it will be better positioned for observation than during its solar pass, when glare and geometry became complicated measurements. Telescopes like the James Webb Space Telescope can target it for spectroscopic analysis, breaking down the light into its component wavelengths to identify specific molecules and isotopic ratios. Those data could determine the exact composition of the ices, the presence of organic compounds, and potentially even isotopic signatures that fingerprint the object's formation environment. Isotope ratios of elements like oxygen, carbon, and nitrogen vary depending on where and when material condensed in a protoplanetary disk. Measuring those ratios in 3IATLAS could reveal whether its parent system had a chemistry similar to our own or something distinct, providing clues to the diversity of planetary formation conditions across the galaxy. Scientists also plan to continue monitoring the object's trajectory and physical evolution as it moves outward from the Sun toward its next milestone, a close flyby of Jupiter on March 16, 2026. The Jupiter encounter offers another observational window and a natural experiment. Jupiter's immense gravity will perturb the object's orbit, accelerating it further, and potentially ejecting it from the solar system on a hyperbolic trajectory, depending on the precise geometry of the approach. Observations during and after the Jupiter flyby could detect additional outgassing or fragmentation triggered by the gravitational stress, providing more data on the object's internal structure and composition. The gravitational interaction might also refine measurements of the object's mass, if tracking is precise enough to detect tiny deviations caused by Jupiter's pull. The question of whether high-quality images from Hubble or Mars Reconnaissance Orbiter exist, but have not been released, is a point of frustration for some in the astronomical community. Space agencies operate on schedules dictated by instrument availability, data processing pipelines, and peer review timelines. Raw data often undergo months of calibration and analysis before public release. However, the delay feeds speculation. In an era of rapid information flow, the absence of high-resolution images feels conspicuous. If such images showed clear evidence of fragmentation, or conversely a pristine nucleus with no signs of activity, either result would be scientifically valuable and would likely be announced. The silence might simply reflect bureaucratic pace, or it might indicate the data are ambiguous, requiring careful interpretation before conclusions are drawn. Until those images surface, researchers rely on data from ground-based telescopes and the Tianwen-1 observations, piecing together a picture from fragmentary evidence. The broader implications of the planetary fragment hypothesis extend beyond 3I-ATLAS itself. If confirmed, it would mark the first time humanity has directly examined a piece of an exoplanet. Exoplanetary science has advanced remarkably over the past 3 decades, with thousands of planets detected around other stars through indirect methods like radial velocity measurements and transit photometry. Those techniques reveal a planet's size, mass, orbital period, and sometimes atmospheric composition, but they do not provide samples. Meteorites offer tangible pieces of asteroids and occasionally Mars or the Moon, blasted into space by impacts and eventually falling to Earth. But an interstellar traveler carrying exoplanetary material into the inner solar system where it can be studied in detail would be an unprecedented scientific windfall. Instruments could analyze its mineralogy, search for organic molecules, and probe its isotopic makeup, building a ground truth dataset for exoplanetary geology that no telescope can match. The possibility of life seeds embedded in the object is more speculative but cannot be entirely dismissed. Panspermia, the hypothesis that life or its precursors can spread between worlds via meteorites or comets, has been debated for over a century. If 3I-ATLAS originated from a planetary system where conditions allowed prebiotic chemistry or even life to emerge, and if fragments from that system were ejected into space, it is conceivable that organic molecules or microbial spores could survive the journey. The interstellar environment is harsh, with intense cosmic radiation and extreme cold, but laboratory experiments have shown that some organic compounds and even certain extremophile microbes can endure such conditions for extended periods. The probability is low, and most scientists consider it unlikely, but the fact it is within the realm of physical possibility means that any detected organic complexity in 3I-ATLAS will be scrutinized for biosignatures. Even if no life is found, the organic inventory could inform understanding of how prebiotic chemistry unfolds in different stellar environments, which bears directly on the question of life's prevalence in the universe. The coincidences are indeed striking when laid out in sequence. An interstellar object with an estimated age exceeding the Sun's arrives in the inner solar system. It exhibits non-gravitational acceleration inconsistent with simple models. Its color changes multiple times, suggesting evolving surface composition or exposure of subsurface layers. It survives a close solar approach without fragmenting and without producing the expected cometary tail. It displays jet structures in irregular directions. Its spectral signature indicates carbon dioxide ice, a compound associated with formation beyond the snowline. Polarimetric data hint at unusual surface properties. Its trajectory lies relatively close to the ecliptic plane. Each detail might have a mundane explanation, but the cumulative weight of the anomalies strains credulity. Pattern seeking is a powerful cognitive tool, but it can also lead to false positives, seeing design where none exists. The scientific method demands skepticism, requiring extraordinary evidence for extraordinary claims. The burden of proof lies with those proposing the object is anything other than a natural interstellar comet, and so far the evidence, while intriguing, does not meet that threshold. Yet the tension persists. The data are forcing astronomers to confront the limits of existing models. Cometary science is mature, built on extensive observations, but it was developed almost entirely from solar system comets. The few interstellar visitors detected so far, 1I Oumuamua in 2017 and 2I Borisov in 2019, were observed only briefly. Oumuamua was particularly enigmatic, displaying extreme elongation or possibly a pancake shape, non-gravitational acceleration without visible outgassing, and a highly reflective surface. Explanations range from a nitrogen ice fragment to a hydrogen iceberg to, in Loeb's controversial proposal, a light sail of artificial origin. The debate over Oumuamua demonstrated how little is known about the population of interstellar objects and the diversity they might exhibit. 2I Borisov appeared more conventional, behaving much like a solar system comet, which was almost reassuring. 3IATLAS now occupies a middle ground, comet-like in some respects but sufficiently anomalous to provoke deeper questions. The notion that 3IATLAS might be a relic from a long-destroyed exoplanet taps into a narrative that resonates beyond the scientific community. The idea of ancient worlds, shattered and scattered, fragments drifting through the dark for billions of years, carries a poignancy and grandeur that stir the imagination. It evokes themes of impermanence and cosmic timescales, the humbling realization that entire planetary systems can rise and fall over eons, leaving only debris as epitaphs. If the hypothesis holds, then studying 3IATLAS becomes an act of archaeology on a galactic scale, reconstructing a lost world from a single shard. The emotional weight of such a discovery might influence public and even scientific perception, which is why maintaining rigor is critical. The hypothesis must stand or fall on evidence, not on its narrative appeal. The role of institutions like NASA and ESA in this investigation cannot be understated. These agencies command the instruments and expertise necessary to extract maximum information from fleeting opportunities like the December flyby. Coordinating observations across multiple telescopes, both ground-based and space-based, requires logistical planning and international collaboration. The scientific return depends on choosing the right targets for limited observing time. James Webb, with its infrared sensitivity, is particularly well suited to detecting and characterizing ices and organic molecules that emit in the infrared spectrum. Hubble's high-resolution imaging in visible and ultraviolet wavelengths can reveal fine structural details and monitor changes over time. Ground-based observatories equipped with adaptive optics can complement space telescopes, providing additional temporal coverage and spectroscopic data. The combined dataset will be far richer than any single instrument could provide alone. The trajectory calculations that place the object's origin 7.5 billion years in the past rely on integrating its motion backward through the galaxy, accounting for the gravitational influences of stars it passed and the overall galactic potential. The galaxy is a dynamic environment. Stars orbit the galactic center in complex patterns, and the gravitational landscape shifts over millions of years as stellar populations evolve. Backtracking an object's path over billions of years accumulates uncertainties. Small errors in measuring the current velocity or position compound over time, making the reconstructed path increasingly speculative the farther back it is traced. The 7.5 billion year figure is an estimate, possibly accurate within a billion years or so, but not precise. Still, even with uncertainty, the general conclusion holds. This object is old, predating the solar system, and it formed around a different star under different conditions. That distant star might still exist, aged and dim, or it might have long since exhausted its fuel and collapsed into a white dwarf, neutron star, or even a black hole, depending on its initial mass. The protoplanetary disk that gave birth to 3IATLAS would have dissipated billions of years ago, its dust either accreted into planets and asteroids or blown away by stellar winds. The planetary system, if it fully formed, might still be there, evolved, and perhaps harboring life. Or it might have been disrupted, planets ejected or consumed, leaving only scattered remnants. The distance between stars means that even if astronomers could identify the approximate region of the galaxy where 3IATLAS originated, pinpointing the exact parent system would be nearly impossible without far more detailed trajectory data than currently available. The object is a messenger without a return address, offering clues to its origins, but no direct link back to the source. The concept of diagenesis, the alteration of materials through heat, pressure, and chemical processes after initial formation, is central to the planetary fragment hypothesis. On Earth, sediments deposited on the ocean floor are buried over time, compressed by the weight of overlying layers, heated by geothermal gradients, and chemically altered by fluids percolating through pore spaces. Clay minerals transform into harder forms, organic material is converted into hydrocarbons, and the loose sediment lithifies into solid rock. If a rocky planet or large planetesimal in another system underwent similar processes, its interior would develop a stratigraphy, layers with distinct chemical and physical properties reflecting the conditions under which they formed and were subsequently modified. A fragment from such a body would carry that layered signature. As solar heating penetrates the surface of 3IATLAS, it might be encountering boundaries between layers, triggering outgassing events as it reaches pockets of volatile rich material trapped between more refractory strata. The mention of polarimetric properties deserves elaboration. Polarimetry measures how light's polarization state changes upon reflection or scattering from a surface. Smooth surfaces and rough surfaces scatter light differently, as do surfaces covered in fine dust versus solid rock. Icy surfaces have characteristic polarimetric signatures that differ from rocky or metallic surfaces. Analyzing the polarization of sunlight reflected from 3IATLAS can provide information about the texture and composition of its surface at scales finer than direct imaging can resolve. If the polarimetric data show properties inconsistent with typical cometary surfaces, which are generally dusty and porous, it might suggest a denser, more consolidated material, possibly consistent with a rocky fragment. However, polarimetric interpretation is complex depending on surface roughness, particle size distributions, and viewing geometry, so definitive conclusions require careful modeling and comparison with laboratory measurements of analog materials. The irregular jet directions captured by Tianwen-1 could also be explained by the object's rotation state. Cometary nuclei often rotate with periods ranging from hours to days, and the rotation axis might not be aligned with the orbital plane. As the nucleus spins, different regions are illuminated by the sun, and if volatile rich patches are distributed unevenly across the surface, gas jets will activate and deactivate as those patches rotate into and out of sunlight. The jets would appear to shift direction over time, and if the rotation is complex, perhaps a tumbling motion rather than simple spin, the pattern could be quite irregular. High-cadence imaging over several rotation periods could map the active regions and constrain the rotation state, but such observations require sustained telescope time and favorable viewing conditions. The question of why NASA has not released high-quality Hubble or Mars Reconnaissance Orbiter images might have prosaic answers. Hubble's schedule is intensely competitive, with observing time allocated through peer-reviewed proposals submitted months or years in advance. If 3IATLAS was targeted, the data might be proprietary to the proposing team for a period, allowing them to analyze and publish results before public release. Mars Reconnaissance Orbiter is primarily designed to image Mars, not deep space objects, though its instruments could in principle be pointed at 3IATLAS if positioned appropriately. The spacecraft's orbital mechanics and instrument constraints might limit such observations. Alternatively, the data might exist and be undergoing processing, or they might have been acquired but show nothing particularly revelatory, delaying public announcement until a comprehensive analysis is complete. The December 19th flyby distance of 270 million kilometers, while substantial, is within the reach of modern infrared and optical telescopes. James Webb can detect objects far fainter and more distant, and 3IATLAS, although small, reflects and emits enough light to be observable with integration times of minutes to hours. Spectroscopic observations can identify absorption and emission features corresponding to specific molecules. For instance, present, carbon dioxide ice has strong absorption bands in the infrared around 4.26 micrometers. Water ice absorbs at different wavelengths. Organic molecules produce complex spectra with multiple features. By comparing the observed spectrum with laboratory reference spectra, astronomers can determine which compounds are present and in what relative abundances. Isotopic ratios require higher spectral resolution, but are feasible for bright targets or with sufficient integration time. Detecting a deuterium to hydrogen ratio different from solar system values, for example, would strongly indicate the object formed in a chemically distinct environment. The March 16, 2026 Jupiter flyby will occur when the object is moving outward, already well beyond Earth's orbit. The distance at closest approach to Jupiter and the geometry of the encounter will determine how much the planet's gravity alters the trajectory. A close pass could boost the object's velocity substantially, sending it on a hyperbolic orbit that will carry it out of the solar system over the coming centuries. A more distant pass might merely deflect the trajectory without ejecting it. Precise tracking before, during, and after the encounter will allow astronomers to measure Jupiter's gravitational influence and, by extension, refine the estimate of 3IATLAS's mass. If the mass can be combined with size estimates from imaging, the bulk density can be calculated, providing clues to whether the object is primarily icy, rocky, or a mixture. The possibility that 3IATLAS could revolutionize understanding of exoplanetary geology is not hyperbole. Current exoplanet studies rely on remote sensing, inferring composition and structure from transit spectra, thermal emissions, and dynamical measurements. Direct samples from an exoplanetary body, even a fragment, would anchor those inferences with empirical data. Mineralogy, the study of crystalline structures and chemical compositions of minerals, could identify which rock-forming processes occurred. The presence of hydrated minerals would indicate water was present at some point. Carbonate minerals would suggest carbon dioxide interacted with liquid water or other fluids. Organic molecules could range from simple hydrocarbons to complex polymers, each telling a story about the chemical evolution of the environment. Even negative results, such as the absence of expected compounds, would be informative, constraining models of planetary chemistry. The speculation about life seeds, while tantalizing, faces significant hurdles. Interstellar space exposes any organic material to cosmic rays, high-energy particles that break molecular bonds and degrade complex structures. The timescales involved are immense. Even if a fragment was ejected from its parent system relatively recently in geological terms, say 100 million years ago, that is still an enormous duration for organic molecules to survive unprotected radiation. Some molecules, particularly those locked within mineral matrices or shielded by meters of overlying rock, might endure, but surface organics would likely be heavily damaged. Laboratory studies have shown that amino acids and nucleobases can survive under simulated interstellar conditions for limited times, especially if embedded in ice. But the viability of actual biological material like spores or cells over millions of years remains doubtful. Nevertheless, the detection of amino acids, sugars, or other prebiotic molecules would be extraordinarily significant, providing insight into the universality of organic chemistry and the potential for life's building blocks to be distributed across the galaxy. The narrative of a destroyed exoplanet carries implicit drama. What caused the destruction? Gravitational interactions are a leading candidate. Giant planets migrating inward through a planetary system driven by interactions with the protoplanetary disk or dynamical instabilities can scatter smaller bodies, ejecting some into interstellar space. Stellar encounters, where another star passes close to a planetary system, can gravitationally perturb orbits, destabilizing the configuration. In extreme cases, a planet could be torn apart by tidal forces if it strays too close to a star or giant planet, the differential gravitational pull across the body exceeding its structural strength. Collisions between planets, though rare, are possible during the chaotic early phase of system formation when orbits are still settling. Each scenario leaves different signatures. A tidal disruption might produce a stream of debris, with similar compositions but different sizes. A collision could mix materials from both bodies, creating a heterogeneous mixture. Gravitational scattering would eject a range of objects, from small fragments to whole moons, with velocities depending on the encounter geometry. The age estimate of 7.5 billion years places the formation of 3IATLAS in the epoch when the Milky Way was approximately half its current age. Star formation was more vigorous then, and the galaxy's metallicity, the abundance of elements heavier than hydrogen and helium, was lower on average than today. Stars form from collapsing molecular clouds, and the chemical composition of those clouds determines the composition of the resulting star and its planetary system. Early stars, formed from more primordial material, have fewer heavy elements, which affects the types and abundances of planets that form. Rocky planets require sufficient quantities of silicon, iron, magnesium, and other metals. Giant planets benefit from cores of rock and ice that can gravitationally capture hydrogen and helium. A planetary system 7.5 billion years old might have a different elemental mix than the solar system, potentially affecting the chemistry of any planets and the composition of fragments like 3I-ATLAS. Measuring the object's isotopic and elemental abundances could provide a snapshot of galactic chemical evolution, a data point from an era otherwise accessible only through indirect astronomical observations of distant stars. The reference to the object's trajectory being close to the ecliptic plane is intriguing but requires careful interpretation. The ecliptic is the plane of Earth's orbit around the Sun, and the orbits of the major planets lie roughly in this plane, a consequence of their formation from a flattened protoplanetary disk. Interstellar objects arriving from random directions in the galaxy should have inclinations distributed uniformly, meaning they are equally likely to approach from any angle. The fact that 3I-ATLAS has a relatively low inclination might be coincidence, a simple result of small number statistics with only a few interstellar objects detected so far. Alternatively, if there is a slight bias in detection toward objects with lower inclinations because they spend more time near the ecliptic where surveys are concentrated, that could explain the observation without requiring any special property of the object itself. Ascribing significance to the low inclination without more data is premature, but it is the kind of detail that, combined with other anomalies, feeds speculation. The description of 3I-ATLAS as a stealth comet, outgassing primarily carbon dioxide, which sublimates without leaving much dust, is a plausible natural explanation that fits several observations. Carbon dioxide ice transitions directly from solid to gas at temperatures around 150 Kelvin under vacuum conditions, far colder than water ice, which sublimates at roughly 200 Kelvin. A comet rich in CO2 and poor in water and dust would begin outgassing at greater distances from the Sun, but the gas would be less visible than water vapor, which produces the bright hydrogen clouds seen in typical comets. Dust reflects sunlight efficiently, creating the bright tails that make comets spectacular. A low-dust comet would be much fainter. If the viewing geometry aligned the gas tail edge onto Earth, it would appear compressed and faint, possibly invisible to all but the most sensitive instruments. Subsequent observations might catch the tail from a better angle, or the outgassing rate might change as different regions of the nucleus become active, explaining the variable appearance. This explanation requires no exotic mechanisms or alien origins, only a composition at the tail end of the cometary distribution. However, The stealth comet model struggles with some details. The rapid brightness increase and the multiple color changes are harder to explain with simple compositional variation. If different ices sublimate at different temperatures, exposing layers as the surface erodes, one might expect color changes, but the sequence and timing would need to match the object's heliocentric distance and solar illumination history. The non-gravitational acceleration also requires the outgassing to produce thrust, which implies significant mass loss even if it is not visible as dust. The absence of a clear tail despite substantial acceleration suggests the gas is either very diffuse or oriented in a way that escapes detection, both of which are possible, but add additional conditions to the explanation. Each added condition reduces the probability that all are met simultaneously by chance. The role of Avi Loeb in the discourse around 3IATLAS, as with Oumuamua, is double-edged. His willingness to publicly discuss unconventional hypotheses brings attention to the objects and the science, engaging broader audiences and encouraging open-minded inquiry. Critics argue he crosses into speculation that is insufficiently grounded, lending credence to ideas that lack supporting evidence and potentially misleading the public. The balance between exploring all possibilities and maintaining scientific discipline is delicate. The scientific process thrives on creative hypotheses, even outlandish ones, as long as they are testable and subjected to rigorous scrutiny. Loeb's comments about propulsion mechanisms or navigational aids are framed as speculative, acknowledging that natural explanations are more likely, which is the appropriate stance. The controversy arises when media coverage amplifies the speculative elements, sometimes omitting the caveats, leading to sensational headlines that distort the underlying science. This dynamic reflects broader challenges in science communication in an era of rapid information dissemination and selective attention. Emily Saunders' characterization of 3IATLAS as a fragment from another star system with radically different conditions is more grounded, focusing on the scientific opportunity rather than speculative extremes. Her emphasis on deciphering the object's composition and history aligns with mainstream investigative goals. Use the available data to reconstruct the environment of origin, identify the physical and chemical processes that shaped it, and integrate that knowledge into the broader understanding of planetary systems. Whether the object is a comet or a planetary fragment, the methodology is the same. Spectroscopy, imaging, dynamical modeling, and laboratory comparison of materials all contribute to building a coherent picture. The difference lies in the interpretation of the results and the implications for what is known about interstellar populations and planetary formation. The absence of debris around 3IATLAS after perihelion is notable. Comets often shed boulders and dust grains that can be detected as co-moving objects or trails. The fragmentation of comets, like Schwarzmann-Wachmann 3, has been extensively studied, revealing how structural weaknesses lead to breakup and the subsequent evolution of the fragments. If 3IATLAS was on the verge of structural failure, one might expect to see small pieces separating from the main body, creating a debris field detectable in high-resolution images. The fact that images from Mars orbiters and ground telescopes show gas jets, but no discrete fragments, suggests the nucleus remains intact. This could indicate a strong internal structure, possibly cemented by processes beyond simple ice cohesion. Refractory materials like silicates or carbonaceous compounds can provide structural support that pure ice lacks. A matrix where ice and rock are intimately mixed, or a layered structure with rocky shells could resist fragmentation better than a fluffy ice ball. The greenish glow transitioning to blue is a spectroscopic signature that depends on excitation mechanisms and molecular abundances. Diatomic carbon, responsible for green emission, forms when organic molecules are photodissociated by ultraviolet sunlight. Carbon monoxide and carbon dioxide ions, which can emit in the blue, arise from ionization processes driven by solar UV and the solar wind. The sequence of colors might reflect the progressive erosion of surface layers. Initially, organic-rich ice on the surface is destroyed, releasing diatomic carbon and producing green emission. As solar heating penetrates deeper, exposing CO2-rich layers, ionization becomes the dominant process, shifting the emission to blue. If this interpretation is correct, the color evolution maps the internal structure, providing a vertical cross-section as sublimation removes material layer by layer. Future spectroscopic monitoring, tracking specific emission lines over time, could test this model. The challenge of verifying the planetary fragment hypothesis lies in the difficulty of proving a negative. How can one definitively show that 3I-ATLAS is not just an unusual comet, but rather a piece of an exoplanet? The key would be finding features incompatible with cometary formation, but expected in planetary contexts. For example, minerals that require high-pressure conditions to form, like certain pyroxenes or olivines found in Earth's mantle, would be a smoking gun, as such minerals do not form in low-pressure cometary environments. Isotopic anomalies inconsistent with any known solar system process would also be compelling, indicating the object formed in a chemically distinct setting. The presence of a layered internal structure, directly imaged through radar or seismic techniques if a mission could be mounted, would support the hypothesis. Without such definitive markers, the distinction might remain ambiguous, with proponents and skeptics interpreting the same data through different frameworks. The possibility of mounting a dedicated mission to 3I-ATLAS is remote in the near term. Space missions require years of planning, funding, and development. By the time a spacecraft could be designed, built, and launched, the object might be far from the Sun, receding into the outer solar system or beyond, making rendezvous prohibitively expensive in terms of fuel and time. Rapid response missions to interstellar objects have been proposed, with spacecraft designed to be launched on short notice when a target is detected, but no such system is currently operational. The best opportunity for detailed study remains remote observation during the December flyby and the subsequent months as the object remains within range of powerful telescopes. If the data from those observations prove sufficiently intriguing, they might motivate future investment in interstellar object intercept capabilities. But for now, astronomers must rely on photons, not probes. The broader question raised by 3I-ATLAS and its predecessors is how common interstellar objects are and what diversity they represent. Estimates based on detection rates suggest that interstellar objects pass through the inner solar system regularly, perhaps several per year, but most go undetected because they are small, faint, or oriented such that they are not easily distinguished from asteroids and comets. Improved survey telescopes, like the Virasi-Rubin Observatory currently under construction, will dramatically increase the detection rate, potentially identifying dozens or hundreds of interstellar visitors per year. A larger sample will reveal whether the anomalies seen in Oumuamua and 3I-ATLAS are rare outliers or represent a significant fraction of the interstellar population. If many interstellar objects show unusual properties, it will force a reevaluation of models for how planetary systems evolve and what kinds of debris they eject into the galaxy. If most are mundane comets and asteroids indistinguishable from solar system counterparts, then Oumuamua and 3I-ATLAS will be remembered as exceptional cases requiring special explanations. The idea that planetary systems regularly eject material into interstellar space is well established. Dynamical simulations of solar system formation show that the early phases are chaotic, with planetesimals scattered in all directions as the giant planets migrate and settle into stable orbits. A significant fraction of the original mass is ejected, populating the galaxy with a vast reservoir of wandering objects. The Oort cloud, the distant shell of comets, surrounding the solar system is thought to contain trillions of objects, and some fraction of those will be perturbed into interstellar trajectories by passing stars or galactic tides over billions of years. Every planetary system likely has a similar reservoir, continuously leaking material into the interstellar medium. The galaxy is thus filled with a mixed population of planetary debris from countless systems, a cosmic ocean of fragments carrying the chemical and geological signatures of their diverse origins. 3IATLAS is one drop in that ocean, brought briefly within reach by the gravitational currents of the Milky Way. The concept of a time capsule from another star system is evocative. The object has traveled for billions of years, shielded from the active processes that reshape planets and asteroids within solar systems. It has not been heated by a sun, save for its recent perihelion pass, nor has it collided with other bodies or been altered by atmospheric weathering or geological activity. It is frozen in a state reflecting its formation and early history, preserved by the cold and isolation of interstellar space. Studying it is akin to opening a geological sample from an alien world, uncontaminated by solar system processes. The mineralogy, the isotopic ratios, the organic inventory, all are snapshots of conditions in a protoplanetary disk billions of years ago, offering a direct comparison to models and a test of whether planetary formation follows universal rules or exhibits significant variability. Encountering a fragment from another world, if verified, would reaffirm the universality of physical laws and the interconnectedness of the galaxy, where material drifts endlessly between stars. It would evoke awe and humility, reminding humanity of its limits and inspiring the pursuit of knowledge from rare cosmic messengers. Yet questions abound. The composition and layering of 3IATLAS, its rotation, survival past perihelion, color changes, and trajectory, all awaiting December's crucial observations. These data may clarify whether the object is an ordinary comet or something more exotic, though ambiguity could fuel debate for years, as seen with pulsars or gamma-ray bursts. Public fascination with such discoveries sustains funding and engagement, but also pressures scientists to balance excitement with rigor. Observing 3IATLAS poses immense technical challenges: precise tracking, faint signals, limited telescope time, and coordination across observatories. Still, advances in adaptive optics and rapid scheduling make joint campaigns possible. The ion tails seen could arise from solar-wind interactions, though irregular patterns might hint at magnetic turbulence. Speculation about propulsion remains hypothetical. Without evidence of control, natural outgassing remains the simplest explanation. If evidence ever confirmed artificial origins, the implications would be civilization shifting, proof of extraterrestrial intelligence and technology. Yet extraordinary claims demand extraordinary proof, and nothing yet justifies abandoning natural explanations. The December flyby will allow detailed infrared spectroscopy, with instruments like James Webb revealing ices, organics, and isotopic ratios that could trace the object's birthplace. Divergent isotope ratios might mark it as interstellar. Familiar ones would tie it to known cometary processes. Later, the 2026 Jupiter flyby will refine trajectory and density estimates, revealing mass and structure. Should the object escape the solar system, it will resume its endless journey, perhaps one day observed by others elsewhere. Even without images, its light curves and spectra already hint at complexity. If its chemistry lies at the extreme edge of known variation, it challenges but does not overturn scientific understanding. The investigation unites cometary science, planetary formation theory, and astrochemistry, demonstrating the collaborative strength of modern astronomy. Whether 3IATLAS proves typical or exceptional, its study deepens humanity's grasp of cosmic processes and tests our methods of inquiry. If anomalies persist, they will drive new instruments and missions. If resolved, They will refine existing models. The mystery's depth will depend on the data, whether it points to a rare natural fragment, a piece of alien geology, or something beyond imagination. Whatever the outcome, it reminds us that the universe's lessons await those patient enough to listen. As a lone traveler from the stars passes briefly within